All right, guys. Good afternoon or good morning. I guess it's still morning here. Um, I want to finish off chapter 2 today. So what I figured is I'd hit another example or so. Try to hit some of the trickier things that can crop up. Um, then I figured I would entertain some questions. If you have any questions about homeworks, we'll hit some of those. But in terms of the big concepts from chapter 2, we're mostly done. So hopefully you guys are getting kind of a sense of the lay of the land here. Um, but when it comes to these one-dimensional kinematics problems, there's a couple more things that you have to be generally aware of. Another tricky situation that you can sometimes run into is something like you might see in an example like this. This is an example that I do every year. Pay attention, it could save your life. So here's the scenario. Let's presume that you are out, taking a nice, pleasant jog. So here's you. And let's assume, for the sake of argument, that you are already running as fast as you can run. Let's say that you're running with a velocity of, let's say, 6 meters per second to the right. And as you take your pleasant jog, you look back over your shoulder and you see, waiting in the wings, a big, mean, hungry velociraptor. That velociraptor is, let's say, 10 meters behind you, and he looks really hungry. I've had before people, when I've done this example, have asked me, what's a velociraptor? Which I find shocking that you've never seen a Jurassic Park movie in your life, but whatever. So this big, mean, nasty velociraptor sees you and decides that you look delicious. And so what's going to happen is this velociraptor is going to charge you. Now, you have one thing going for you right now, and that's, at the moment, the velociraptor is not yet moving. So right now, this velociraptor is sitting here with a velocity of 0. However, they don't call them velociraptors for nothing. They call them that because they are insanely fast. And so while he may be at rest now, he's going to have an acceleration of, let's go with 4 meters per second squared. And he is going to come loping after you. So the question that I want to answer in all of this is, how far can you get before this thing catches you? That's important, because if you can't find some sort of safety within that distance, you're gonna die. We don't want that. So how far can you get before it catches you? Well, catches. Getting dyslexic in my old age. All right. So that's the scenario. So this is like any other one-dimensional kinematics problem. You're going to do the same 4 steps you do with any kinematics problem ever. Step 1, right? You're going to draw a picture, which, yay, I've got the starts of 1. 2, you're going to choose a coordinate system and then break down what you know into some kind of inventory. And then based on what you've got available, what information you have, that's going to guide you to equations of motion that you can then use to solve. Now, here's the wrinkle in this problem, right? There are 2 objects that are moving, right? A lot of times when I see students try to set a problem up like this, what they do is they say, aha, I'll choose a coordinate system and I'll call this x equals 0, and I'll call this x equals 10, and I'll let x equals 0 be my starting position and x equals 10 be my final position. And then they put in something for V initial, maybe that they put in that for V initial and that for V final and that for A. And they think they have an an inventory that's set up. But the problem is they've mixed and matched information from the Velociraptor with information from the human, right? Both of them are moving. And so what that means is that I'm going to have to take inventory of both of the objects, because I don't want to just find how long it will take for this guy to go from here to here, because by the time the Velociraptor reaches this location, you're not going to be there anymore. You're running away, right? So to make sense of this problem, we got to kind of think this through a little bit more before we jump in and start trying to throw things into equations, right? So let's think this through. The moment that this guy sees you, you're moving, he's not. So what's going to happen is at first you're traveling faster than him. So at first you're pulling away. But very quickly he's going to pick up speed and he'll eventually start to outpace you. And what that means is that as time goes on, he's getting closer. He's getting closer. He's getting closer. And so somewhere over here, and I'm not really sure where it is, there's going to be a spot where the Velociraptor catches you. And at that point, you hopefully will find something to safety. Otherwise, blood everywhere. So, if I'm trying to do an inventory for this problem, the trick is for the Velociraptor, it's going to start here and end here. For you, you're going to start here and end here. So I've got two separate inventories I'm going to do. Let's choose a coordinate system. Somewhere on this picture, I have to call x equals 0. And I kind of like calling this x equals 0. And of course, the positive direction will be to the right. So if I do that, then what's going to happen is you are starting off at x equals 10 meters. So if I do the Velociraptor inventory, I've got 6 things to keep track of: where he starts, where he finishes, his original velocity, his final velocity, his acceleration, and the time that elapses between point A and point B. Now, for the Velociraptor, where he starts, his initial position is x equals 0. Now, his final position is wherever he is when he eventually catches you. And I'm not really sure how far away this is. So x final is unknown. For V initial, he starts over here. We said he started at rest. So that's 0. His final position is however fast he's going when he catches you. And I'm not really sure how fast he's going to be going. All I know for sure is it'll be faster than 6 meters per second, because if he wasn't traveling faster than you, he never would have caught you, right? So something faster than 6, but I'm not sure how much faster. His acceleration was specified in the problem as 4 meters per second squared. And the time it takes to go from here to here, I don't know. So that's unknown. Now, what about you? I could do something similar with you. Find your starting position, your ending position, your starting velocity, your ending velocity, your acceleration, and the time that elapses. Now, if this is x equals 0 over here, you're starting 10 meters ahead of that. So your starting position is going to be x equals 10 meters. X final is going to be wherever you are when the Velociraptor finally catches up with you. I don't know where that is. Now, your starting velocity, we said, was 6 meters per second. Now, what about your ending velocity? Well, we said in the setup that you were already running as fast as you can, and you're certainly not going to see a Velociraptor chasing you and slow down, because that's stupid. So you're going to still be running the same speed at the end. Notice if your velocity hasn't changed, that implies that your acceleration must have been zero, right? If your velocity had been changing, your acceleration would be non-zero, but zero acceleration means you're traveling at a constant speed. And of course, the time to go from here to here is unknown. So my normal plan when I get to this next step of a kinematics problem is I've got these inventories, and I usually look to see if I can find an equation of motion that includes the thing that I'm solving for, but avoids anything else that I don't already know. So the first thing I need to figure out is, what the heck am I trying to figure out here? Well, the question asks, how far can I get? In other words, I need to know how far this is. And in order for me to figure that out, I need to know where this happens. So the final position is the thing I'm going to have to figure out. Well, the final position is this. So this is what I'm looking for. And so if I'm just looking at the inventory for you, and I'm thinking about those 4 kinematic equations of motion, I'm looking for an equation that has x final, but does not have t. Well, there are 4 of them, but the one that doesn't have time in it is this guy. So my first inclination might be to try to leverage this equation to solve for x final. But I'm going to run into a problem when I try to do that. And the problem I'm going to run into is, in this particular example, my acceleration is 0. And if I plug in 0 for a, I'm going to have 0 times all of this stuff. This whole term gets wiped out. And unfortunately, when that term gets wiped out, it's going to take the thing I'm trying to solve for with it. Suddenly, I can't solve it anymore. I end up with v final squared equals v initial squared, which, no duh, it totally is true, right? 6 squared does in fact equal 6 squared. So yay, the equation is true, but it's not very helpful. So trying to solve this inventory for x final, that's a bust. It won't work. I've got to try something different now. My plan A is a failure. Now, one thing I recognize is that the final position of u is the same as the final position of the velociraptor. So in principle, this is the same as that. If I could solve the velociraptor and find where he ends up, I will be able to know by default where you ended up, because he's ending up eating you. The problem, though, is that when I look at the velociraptor inventory, I have way more things in it that I don't know. I don't know the time. I don't know the final velocity. I don't know the final position. I've got very little information there. And what's going to happen to me is, if I try to solve this equation, I won't even be able to find an equation of motion that has x final, but not v final or t, right? This one wouldn't work because it's got x final and v final in it. So that's 2 unknowns. That's a bust. The position equation, that's not going to work because it's got x final in it. I don't know that. It's got time in it. Don't know that. So 2 unknowns. That sucks. The velocity equation, that's not going to work because the thing I'm looking for doesn't even appear. And even if it did, I still run into the problem of, I don't know v final, I don't know t. So even then, there's 2 things in it that I don't know. And the useless equation, I'm mostly just using this as an excuse to write all 4 of them out, since most of you guys are probably still learning them. But the useless equation is still useless because I don't know this, I don't know this, I don't know this. That's 3 things in one equation that I don't know. That's definitely not solvable. So we're going to have to try something different. And so when you run into a problem like this with a 2-body problem where there's 2 objects moving around, one thing that you probably are going to have to do is to solve a system of equations, right? I'm going to have to get two equations, each of which have two unknowns, and then use the equation from one of the objects and the equation from the other object and algebraically combine them to solve for whatever it is I'm solving for. So how do I know which equations to start with? Well, one thing that helps me figure that out is I think about what these two inventories have in common. And the thing that I know they have in common is that the velociraptor and the person both end up in the same location. So x final has to be the same value for both of them. And the time it takes for him to go from here to here should be the same as the time it takes for you to go from here to here. So these times are also in common. And once I notice a situation like that, where I have two things shared across those two inventories, my strategy is going to change. I'm no longer going to look for an equation of motion that doesn't have either of those things in it. I'm going to look for an equation of motion that has both of those things in it. I want to have x final. I want to have t. But I still want to avoid anything else that I don't already know. So notice v final, I don't know v final for the velociraptor. So I'm going to go out of my way to avoid using any equations that have the final velocity in it, because that'll screw me up. And when I look at it this way, v final does not appear in this equation. So what I'm going to do is, it's got x final, which is I need for both. It's got t, which I need for both. So the way to solve this problem is to take this equation, and I'm going to kind of customize the generic equation for each of the two inventories. I'm going to get one version of this equation from the velociraptor inventory and a second version of that equation from the person inventory. That's going to give me two equations and two unknowns. And once I get there, that turns into an algebra problem. So let's try that. I'm going to take this equation and I'm going to replace x final with whatever x final is. I'll leave that as a variable. X initial, I'll swap out with whatever x initial is, and so on and so forth. Let's try it out. So when I do the equation for the velociraptor, here, let's do this. Let's put this guy in easy view while I do this so that we can see this all at one time. So for the velociraptor, I need x final, which is something, right, equals x initial, but that's 0, so I'm not going to write it, plus v initial times t, but v initial is 0, so 0 times t is still 0, not going to write it, plus 1/2 times the acceleration, which is 4, times the time squared, which is, I don't know. So the equation I get for the velociraptor is this. Of course, 1/2 times 4 is 2. So this equation tells me where the velociraptor will be as a function of time. At time 0, he's here. At time 1 second, he's going to be 2 times 1 squared is 2. He'll be 2 meters this way, right? And so on and so forth. So I plug in a value for t. This will tell me where he is. But I don't know what time to look for yet, so I can't solve this yet. I have two unknowns. Now, what about the equation for the person? I'll do the same trick, but I'll use this inventory. So for that one, x final is, I don't know. X initial is 10 meters. Plus v initial times t, so it's 6 times t. Plus 1/2 at squared, but a for the person is 0, which means that whole last term cancels out. So that's the equation for the person, u. So now I've got two equations and two unknowns. And in order to solve this, at this point, it turns into a math problem, right? I want to solve these two equations, and the first thing that I notice is that if x equals this garbage, but x also equals this garbage, then by the transitive property, that assumes that this equals this. So if I do that, it eliminates x, and I only have t's. So I'll have 2t squared is going to equal 10 plus 6t. So at this point, since I've eliminated all the x's, I'll be able to solve for the time that it's going to take for the velociraptor to travel from here to here. Now, once I know how much time it takes, I can go back and plug into either of these two equations and see where the velociraptor is when that occurs. So I'm going to have to do an extra step because I'm solving for t first rather than x. We're going to keep it that way. In principle, if I wanted to be super, super clever, I could try solving this for t, getting an expression and plugging it into the other equation. But the algebra on that is way, way messier. It's easier to do it this way. So I got to solve this for t. Problem. T appears once squared and once not squared. This is a quadratic equation. And the way you solve a quadratic equation is you get it into standard form. Standard form for a quadratic is ax squared plus bx plus c equals 0. So I need to get everything on one side of the equal sign. So let's just take all this garbage over here, move to the other side. So now I've got 2t squared minus 6t minus 10 is equal to 0. So now when I look at that, what I recognize is that I'm in standard form. I can solve those one of two ways. One is by factoring, but 9 times out of 10, stuff won't factor. This might factor, I'm not even sure. But the other way is the quadratic formula, and I'm just going to use that. So the quadratic formula says that x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. The number of students that I have that can't memorize equations in physics for anything, but they know this thing by heart from like junior high is crazy. But that's the quadratic formula. And all I've got to do is identify a, b, and c. And a, b, and c are the coefficients on my variable terms. And in this case, my variable is not x, it's t. So what's going to happen is a is the thing that's times t squared. B is the thing that's times t, which notice is not just 6, it's negative 6. And c is the part that doesn't have the variable attached to it at all. So negative 10. So my value for t is going to be negative b. So negative 6 is positive 6, plus or minus the square root of b squared, so that's 36, minus 4 times a, which is 2, times c, which is negative 10, all over 2a, so 2 times 2 is 4. And we're good to go. Notice cool thing, minus times a minus becomes plus. That's important because it means we're not going to get a negative underneath the radical. That would be bad because if I had a negative under radical, my only time would be imaginary. Now, what would that mean if I had a negative under the radical? Well, that would suggest that since we're solving for the time that it takes for this guy to catch you, if the only solution to the problem were a negative or so an imaginary time, the answer would be he's never going to catch you. You're going to get away. You'll live to jog another day. Sadly, the fact that I'm not going to get an imaginary answer tells me that there is a definitive time where you will get caught. So if you cannot get to safety within that time, you are going to die. So we solve this. So that's 80 plus 36 is 116. When I square root 116, this is 10.77 under the radical. Notice if I do 6 plus 10.77, that's 16.77, divided by 4 is 4.19 seconds. So one solution is 4.19 seconds. What about the other solution? Well, that would be 6 minus 10.77. That's going to be negative something. And negative time is stupid. Yeah, so you get like negative 1.19. And of course, this is where, even though this is a solution to the mathematics equation, it doesn't correspond to anything physically real. So we have to use a little bit of common sense to say, aha, that answer is dumb and I'm throwing it away. All right. Always check when you solve quadratics, because there will be times where sometimes both solutions might be valid. There might be reasons for it. So you have to think it through, but here we can rule that out. So what this tells me is that it's going to take this velociraptor 4.19 seconds in order to catch you. So if that's the case, what's the answer to the question? Well, after 4.19 seconds, where are you going to be? I could plug this value into either of these two equations. I'm going to plug it into this equation because it's simpler. If I take 4.19 squared times 2, I get 35.11 meters. So that's the position of the person when they get caught. So, more caveat, however, pay attention to the phrasing of the question, because sometimes just because you solve for X doesn't mean that's the thing they asked you for. And this is a prime example of that. Because what we just solved for was that the position of this position right here is 35.11 meters. Now, the problem is the question asked, how far can you get? Well, you started here and you went to here. So what the question is asking you is basically, how far is this? But that is not 35.11 meters. It's 35.11 meters from here to X equals 0. So in fact, if this is 10 meters and this is 35.11 meters, the answer to the question would actually not be 35, but instead 25. Do you see how I got that?
Mm-hmm.
Yeah. So that's the idea. So this is what I call a two-body problem. The trick is I had multiple objects moving around, and I had to do inventories for each of them in turn and combine what I had to figure out whatever was asked of me. And those are the two big complications that we can see, is this one where I have multiple objects, and the one from yesterday where we had an acceleration that was changing over the course of the problem. If I see a problem where there are multiple accelerations, I'm going to have to split that problem into multiple parts and use a different inventory for each acceleration. So some of these problems might seem overly complicated, but that's ultimately what we're doing. All right, how do you feel about this? Is this pretty straightforward? You guys know what we're doing?
I understand how we got the answer, but like the fact that we ended up like solving it with a quadratic formula, I think doing it on my own, it would be super difficult for me to like figure out, okay, that's how we get there and that's how we solve it.
Yeah, and that's like, this is one of those things where, you know, it looks easy when I do it, right? Because I've done this a zillion times, right? I've been doing this stuff for like 30 years at this point. It takes practice, right?
Mm-hmm.
So the trick is, like, if you're not sure how to approach it, start with the setup, right? All the important work happens during that initial setup start where you're doing the inventories. And then, you know, once you get there, you know, you look to see, you know, how can I avoid the stuff that I don't care about but don't know, to get equations. And then it's just a matter of working through the math, right? And yeah, sometimes that can be a little intimidating, but don't be afraid of it. And one thing that I'll caution you, right, is like, because the homeworks are graded by the computer, right? You got to get all the stupid details right to get any credit at all for the computer. But you can keep doing it over and over and over again.
Mhm.
When it comes to places like exams, where you're acting under pressure, you're also going to be turning in your work for partial credit. And what's going to happen is much of that partial credit is going to come from, setting it up, getting the inventory, and then generating the equations that you need. And if you get stuck on the math, that's a smaller fraction of what your final answer would be. Just to give you a sense of how I grade stuff for exam purposes, my rule of thumb is that if the problem is worth 20 points, if you get to the point of the problem where it stops being about physics and becomes purely about math, that's at least 14 out of 20 points, right? The last 6 points is, can I do some math? Because this is not a math class, it's a physics class. Math is just a tool that we use, but it's not the point.
Mhm.
So like in this problem that we just did, go back to my camera real quick. So like, where is that? Wrong camera, stupid. There we go. So where's the point where you got there, right? So we labeled the diagram, we figured out, the various positions, we did the two inventories, and the minute that we said, okay, I know that these are the things in common, so I'm going to generate two equations,
Mhm.
and I got to here, right? If this was an exam and I saw you get to here and then do a bunch of crazy stuff that's bad algebra, that's 14 out of 20 points. The last 6 points is just all this garbage. Does that make sense?
Yeah.
So, when in doubt, work through the fundamentals, and hopefully this stuff will come to you after you kind of play around with it a little bit. But
Mhm.
that might be a place where you're going to feel a little bit unsure of yourself at first, but it will get better.
Okay.
I have
Thank
a
you.
question.
Yes. What's the question?
Oh, I was gonna ask. Can you explain how we got to the making the separate equations one last time?
Yeah. So, all right, let's go back to the camera again. All right. I don't know why I have to cycle. Okay, so we set up the diagram and figured out, okay, he starts here, you start here, you both end up in the same place because he's going to eat you, right? We
Got that.
labeled our inventories. And
Mhm.
what we recognized was that the things we didn't know were the X finals, but that's the thing I had to figure out for sure.
Uh-huh.
And then the time we didn't know, we didn't necessarily need to know it. We ended up solving for it anyway, but we didn't need to know it. And then V final for the Velociraptor was unknown. And so the trick was, because these things were in common, what I was going to do is look at my 4 equations of motion and pick an equation that included both this and this, but not this.
Okay.
So that's where we were going. And the thing that we said was, this equation was bad because it doesn't have time in it. So this one sucks.
Mhm.
This equation is bad because it doesn't have X in it. So this one sucks.
Mhm.
This one is bad because even though it has X and it has T, it also had V final, and I'm trying to avoid V final. So
Uh-huh.
this one sucks. So this is my friend. So I'm taking that generic equation and then I'm specializing it for these inventories. So when I do the Velociraptor, X final is, I don't know, let's just call it X final,
Okay.
right? X initial is just flat out 0. So I don't even have to write it.
Okay, so we didn't add that.
Yeah, V initial times T, well, that's 0 times T, but that's still 0. So didn't have to write that either. So the first 2 terms didn't show up for the Velociraptor at all.
Okay.
Then I said, aha, for the Velociraptor, A is 4, so 1/2 times A is 2, so 2 T squared. And that's where the equation for the Velociraptor came from.
Okay.
And then for the person, we did the same deal, right? We went back to this equation and said, X final, don't know it. X initial was, for that one, 10. V initial for that one was 6 times T. And then for the person, the acceleration was 0. So for them, this whole term was 0. So that's where the second equation came from.
Okay. Thank you.
Yeah. But you're always starting with these things here, and then you'll specialize them into the particular specific forms for this one problem based on whatever the inventory was.
Okay, that's
That-
okay.
That's why it
Thank
helps
you.
to list them out like this. It makes it's super easy to rattle them off once you kind of organize the information. You don't
Okay.
have to do this stuff, but I have found that if you don't know what you're doing, it helps to list it. All right. Any other questions about that? That seemed pretty straightforward. I mean, it was not easy, but it was doable. All right, so here's the part where I'm gonna hurt my heart a little bit. Let's talk about homeworks. So I'm pulling those homeworks up. When's that first batch of homeworks due? I think I have it due
Thursday.
Thursday night. Yes.
No,
So
let's do it Thursday at noon.
is it noon? Really?
Yeah, it had PM on it.
That's probably a typo on my part. Yeah, it is. It should be PM or yeah, that's incorrect. I'll try to fix that before that happens. My intent usually is to have the due dates be at like 11:59, just to avoid the confusion between AM and PM. You know, the idea is that if it says it's due on June 4th, when it becomes June 5th, it's late. I will also point out for those of you, there's not many of you, but for those of you who are in other time zones, all the times are Charlotte time, obviously. So if you're in Central, I think I have one person in Central time. You know, it's an hour later here than it is for you. So bear that in mind when you're looking at due dates, because I don't think that Canvas will list it in local time. All right, so if I look at the homeworks, how many of you have cracked those open at all? Some of you.
I did like 2, maybe.
Yeah. Yeah. So anybody got any questions about any of those that like you're looking at it, you have no idea what you're doing? Now is your chance.
I'm about to pull one up that I started yesterday,
Okay.
but so the 2.31 with the intervals. So what I think I was trying to use the example that we did in class with it.
Yeah, because we did something very similar.
Off is that we use different units for it. Like this one has km in hours, and the one we did was miles per hour. So I was wondering, like, and I know it's asking for it in that unit. So I was trying to figure out like how to, I guess, go about it. Like I said, it's more so like a basics thing for me that I'm trying to remember.
Yeah. So yeah, the thing that that you got to know for something like that is let's pull up the version of that so you can see what I'm talking about. So like here's an example. Obviously your numbers will be different from mine.
Mm-hmm.
But if you're doing a problem like this, the thing you want to remember is that units follow the same rules of algebra as anything else. And so for instance, if I've got, you know, a problem where I've got, let's say, a velocity, or how about a distance in miles, so 5 miles, and I divide that 5 miles by, let's say, 30 miles per hour, then the way I would solve that problem is I could do the math with the regular numbers. So 5 divided by 30 is going to be 1/6, right?
Mm-hmm.
Then miles divided by miles per hour. Well, when you divide by fraction, it's the same as multiplying by the reciprocal. So that's like miles times hours over miles. And at that point, miles over miles cancels, and your answer would be in hours.
Mm-hmm.
Right? So, you know, when in doubt, you can do algebra with your units and keep track of what your units are. So for something like this, if the problem wants my answer in kilometers per hour, what I would probably just do is I would convert all of my times that weren't in hours into hours. So like 20 minutes, I convert to hours. 50 minutes, I convert to hours.
That's what I was wondering.
Yeah. And that way, what's going to happen is, you know, if you plug all your units are miles and hours, when you do your average velocity, it will be in, or not in miles, kilometers per hour. If all your distances are in kilometers, all your speeds are in kilometers per hour, and all your times are in hours, they'll come out in kilometers per hour without having to worry too much about it. So
Okay.
yeah, that'd be my first inclination. So like when I see 20 minutes is 1/3 of an hour. 15 minutes is 1/4 of an hour. 31 minutes is 31/60ths of an hour, which is really close to half an hour. But that's what I would do.
Okay. So Rook, just a quick refresher with conversion. So because
Okay.
I took calculus stuff, so when I convert, I have to do the chart thing with it. So I know
have a
it'll
PhD
be
in physics, and I still use the stupid chart thing.
so
It
I
works.
know it'll be 20 minutes over. So it'll be 20 minutes over 60 minutes and have the hour on top.
Yeah. So like, let's say I have 20 minutes, right?
Mm-hmm.
And what I'm doing is I know I'm going to multiply. I would always do like a little thing, right?
Yeah, that's what I do.
Yep. And so what I'm going to do is I'm going to take the conversion factor and put it here. And what I have to remember is, what is that conversion factor? Well, I know that 1 hour is equal to 60 minutes.
Yeah.
And so since I have minutes up top, I'm going to put minutes on the bottom. That way,
Right.
minutes over minutes will cancel. So I'm going to put this on the bottom.
So yeah, 60 minutes on the bottom, then an hour on top.
And then 1 hour on top. And so now I know that I divide by everything on the bottom. So it's 20 divided by 60.
Got you. Okay, I just had to refresh my memory on that.
Yep. Yeah, like I said, to this day, I still do this. I learned this in like high school chemistry or something. And it's still what I do when I'm confused. And sometimes, some of these unit conversions are tricky and people screw them up all the time. Here's an example of one that students 9 times out of 10 will get wrong. I want to know how many cubic centimeters do I get if I have 2 cubic meters? So convert 2 cubic meters into cubic centimeters.
Sorry, hold on. Give me 1 second. You said cubic centimeter into 2 cubic meters? Is that meters?
Yep, but it's cubic meters. Now, what the heck's a cubic meter? Well, you know what a meter stick is, right? It's about, roughly about 3 feet long. So a cubic meter is like a box that's 1 meter on one side, 1 meter on the other side, 1 meter on the third side. So it's a meter by a meter by a meter. By the same token, a centimeter is about, very, very small. 1 inch is about 2.54 centimeters. So a centimeter is very small, and a cubic centimeter is going to be a box that's 1 centimeter by 1 centimeter by 1 centimeter. Turns out a cubic centimeter is the same thing as a milliliter, right? So this is a pretty common thing to have to convert if you're doing like volume measurements, which you do all the time when you're pipetting and stuff like that. So if I have 2 cubic meters, I need to, in converting to cubic centimeters, I know the number is going to be bigger, but the question is how much bigger? So what's the conversion factor?
Would it be the meters part?
Well, what's the conversion between meters and centimeters? That's the one that most of you know.
I don't remember. I'm sorry.
Well, this one's easy to remember because it's centi, right? Same root word as cent, as in the number of cents in a dollar, or century, the years in a century, right? It's 100, right?
Oh,
cent means 100. So there are 100 centimeters.
Oh, so 1 meter, right?
In 1 meter, right? That's the thing everybody should know. Now, if I'm going to convert 2 cubic meters with that same trick, so 2 cubic meters, I'll do the stupid chart thing. Now I want meters to cancel, so I'm going to put 1 meter on the bottom and 100 centimeters on the top. But the problem is I don't have just meters up here. I have meters cubed.
Yeah.
Which means I got to do this 3 times. bad handwriting there. So now it's meters divided by meters divided by meters divided by meters. All the meters cancel. And notice I'm multiplying 2 times 100 times 100 times 100. Well, 100 times 100 times 100 is 1,000,000. So the answer is 2,000,000 cubic centimeters. And that's one that a lot of times people will screw up. They'll know this and they'll multiply by 100 and get the answer wrong by a lot.
Yeah.
Another one that's pretty tricky. Let's say that I want to have 55 miles per hour. And I want to convert that into metric, which is meters per second. So in order to do that, I have to know 2 conversion factors. Well, 3 technically. I have to know that, 60 seconds is equal to 1 minute. I have to know that 60 minutes is equal to 1 hour. I have to know that 1 mile is, I believe it's 1,609 meters. That's probably not one you know off the top of your head. Just for the record, when it comes to like exam type situations, I expect you guys to know the metric system. I don't necessarily expect you guys to know English to metric conversions. So like, you don't necessarily have to know that 1,609 meters is 1 mile. I wouldn't begrudge you if you didn't know that. But if you didn't know how many centimeters were in a meter, that I would probably give you some grief for. Because you're scientists and we use metric. So for this one here, I'd be like, okay, I want miles to cancel. So 1 mile is 1,609 meters. Now I want hours to cancel. So 1 hour is 60 minutes. And then 1 minute is 60 seconds. So the hours will cancel, the miles will cancel, the minutes will cancel, and I'll end up with meters per second. But that means I'm going to take 55, multiply by 1,609, and then divide it by 60 twice. So that's one you'll be doing a lot. So yeah.
I have a question. Why twice?
Well, because the first 60 was you converting hours into minutes.
Mm-hmm.
But if you just did it once, you'd have your answer in meters per minute.
Oh, it has to be per hour, right?
Well, you started off per hour, and I wanted to get per
second. Okay, per second.
So
okay,
I had to convert the minutes into seconds also. That's where the second divided by 60 came from.
Okay.
All right. So, yeah, knowing how to convert units, super, super helpful. But once you've done that, this one is very much like the example we did in class the other day. And the trick is, remember the definition of average velocity is not just average all the V's, because that'll get you the wrong answer every time. But instead, the definition of average velocity, God bless, there we go, is the change in position over time. And so what you're going to have to do is separately figure out how far did this person go. So like if they're going 28 kilometers per hour for 20 minutes, they're going to go 9.33 kilometers, right? How did I get that? I said that since at constant speed, your distance would equal your velocity times time. That's just the formula you learned back in grade school, right? It's like the position equation, but without the acceleration, because the acceleration during that 20 minutes is 0. And we are looking for how far she went. We know how fast she was going, 28. We know the time, 20 minutes or 1/3 of an hour. So I took 28 times 1/3 and got 9.33. So during the first section, she went 9.33 0.33 kilometers. Then during the second part, 51 kilometers per hour for 15 minutes. Well, 15 minutes is a quarter of an hour. So she's going to go another 12.75 kilometers. Right. Then it says she's stopping for 31 minutes. So during that 31 minutes, she's not going anywhere at all. So she's covering no distance from that. And then lastly, she's going 35 kilometers per hour for 34 more kilometers per hour for 55 minutes. 55 minutes divided by 60 is 0.9166 hours. So that times 34 means that during that last 55 minutes, she's going to travel 31.16 kilometers. So if I add those three things together, that's going to give me delta X. That's how far she went.
Well, I have a question. Sorry.
Uh-huh.
So you said you're doing the distance equals velocity times time.
Mm-hmm.
So, oh, you're timesing it. Okay, so did you just time, what's that, 28 by 20, but you put 9.33, like I
didn't multiply by 20 because what I can't do is I can't mix different units for the same thing. I can't mix minutes with hours.
Okay.
So what I did is I converted the minutes into hours.
Oh yeah, you did. Okay, gotcha.
Yeah. So I did 28 times 1/3 because 20 minutes is 1/3 of an hour. And so with each of those, that's what I'm doing. All right. And then when I figure out what to divide by, I'm going to divide by the total time, which is going to be the 1/3 of an hour plus 1/4 of an hour plus 0.5 something of an hour plus 0.916 of an hour, whatever all that adds up to, that's the delta T. So for that, I would include the time for the stop, even though she didn't go anywhere. Does that make sense?
Okay, so in our problem, so I went ahead and converted all of the minutes to hours, right?
Yep.
So for ours, for each part, I would do the 30 times, well, in our problem, the 30 times I did it in decimals, so I did 0.333 hours and do that for each one. And then you said that gives the distance up top, right?
Yeah. Once you add those three distances together, that's the delta X, because that's how far she went in total.
Okay. And then you said for the time, we just basically add up all the time together and that goes on the bottom.
Yep, because that's how long the trip took in total.
Okay.
Yep. So that's the scenario. And again, I don't ask a whole lot of average velocity questions on exams, but when I do, it's usually something like this. And the idea is that if you know what you're doing, you know that you got to find the total displacement and the total time. If you don't know what you're doing, then what you would do is be like, oh, I'm going to take 28 and 51 and 0 and 34 and just all those different velocities and just add them up and divide by 4, and that's the wrong answer. So don't do it that way. All right, anything else you guys are super stuck on?
Not right now. I'm kind of just trying to go through them.
Okay.
Dr. Fleming, did you post the recording from the videos yesterday? Because I didn't see.
I believe so.
I didn't see them in the cloud recordings.
I recorded them locally. If you go to, hang on. I'm glad that you asked that question, because here's what happens. Let's go to screen share. So here's Canvas. This is what Canvas looks like. Go to modules, right? And this is like how things are sort of organized. You can see these are the getting started things. Make sure you've done all of those. If you haven't, you didn't unlock stuff. Here's the class videos and the ones from yesterday.
Okay, gotcha.
Are these. It was in 2 parts. because it got interrupted. So.
Okay.
So, yeah,
Thank you.
yeah, usually I'll record them to the cloud at first, but for whatever reason, it ended up defaulting yesterday to recording it on my device. And so I had a local copy. And usually I'll delete them from the cloud after a while anyway, because there's a limited amount of space in it. But they'll always end up here. So yeah, you can find all the videos, including like the lab, all of them there.
Okay.
All right. So if you don't have any other questions about chapter 2, it's time to move on. And what's going to happen in the next chapter is we're going to make things more complicated, right? Up until now, oh, hang on, sorry. There is one more thing from chapter 2 we have to address before I move on. And that's falling objects. We need to talk about free fall. So if I were to do an experiment, and this is usually a thing I do in class as a demonstration, we're gonna have to make do with the camera. It's not gonna work that great. But if I were doing an experiment where I take, let's say, this piece of paper, and let's get something heavy. I don't have anything heavy. Well, this calculator. And if I were to take them side by side and release them simultaneously, what's going to happen is the calculator is going to fall very rapidly, the paper less so. How come?
The calculator is heavier.
Okay. So why does that matter?
It'll fall quicker.
Okay. So what you're telling me is that things that are heavier will fall quicker than things that are light. Is that what I'm hearing?
Yes.
Okay. So I have bad news for you. That statement is absolutely incorrect, right? The good news is don't feel bad about it, because like some of the most brilliant people in history for 1,000 years thought the exact same thing you just said. They assumed heavy things fall more quickly than light things. Aristotle was totally down for this plan. He was absolutely wrong. And the reason that people thought that, the reason you probably think that, is because you've seen stuff like this where pieces of paper will float gradually to the ground and big heavy rocks will fall like rocks. Feathers will float gradually down. But it turns out that that's not the whole story. And if you're careful about your observations, you can prove that that's not true. And the way to prove it is if I take the same piece of paper, right? And this calculator, if I take the piece of paper and I crumple it up, it didn't get any heavier, right? It's not heavier just because I've crumpled it up. So the weight has not changed one little bit. But now if I take this piece of paper and this calculator and I drop them simultaneously, they fall at the exact same speed. So it's not about the weight. The weight has very little to do with it. Instead, there's something else going on. What did I change when I crumpled the piece of paper up?
It's property. It's physical property.
Yeah, that's one.
Okay, well, more specifically, what physical property are we thinking of?
I can't.
I'll give you a hint. It's the reason why Corvettes are faster than Volvos.
I don't know anything about cars, so I'm sorry.
Yeah.
Aerodynamics.
I'm sorry. That was a bad analogy for me.
It's all about aerodynamics, right? So here's what's going to happen. When the paper was out flat, as the paper falls, it's not falling in a vacuum, right? There's air underneath it, right? And what happens is as it falls, it's got to push the air out of the way. And when the paper is flat like this, that's very difficult. right? The air getting out of the way pushes back against the paper and it slows it down. And so it falls more slowly than you would otherwise expect. Meanwhile, when I crumple it up, what's going to happen is there's less air underneath it. The air doesn't have to go as far to get out of the way, which means the paper doesn't have to push very hard on it to get it out of the way at all. So the effect of the air resistance as it moves through is considerably smaller for this. And what's going to happen is, for both of these objects, the air resistance is basically negligible. It makes hardly any difference at all. It's only super noticeable for this piece of paper because it's so broad and it's so light. So things like feathers that have lots of surface area but not a lot of weight, the air resistance is very noticeable. But for most objects, the air resistance is so tiny, you'd have a hard time measuring it if you wanted to. And so as a consequence, if you take away the effects of air resistance, everything falls at the exact same rate. True story. During the Apollo moon landings, one of the experiments that they did was they traveled to the moon where there is no air, there is no atmosphere at all, and they took a feather and a wrench, right? The wrench was pretty hefty, and they took that feather and the wrench, they dropped them simultaneously on the moon, and as you could watch, the two of them fell side by side all the way down to hit the ground. So take away the effect of air resistance and everything falls exactly the same speed. Now, on the moon, it's slower than it is on Earth, but even on Earth, you could make this work. I've seen videos, and if I could find the video, I'd show it to you, but I couldn't find it the other day, where what they did, it was in an episode of Nova, I think. I'm not sure. Maybe that's why I can't find it. But they took this big tank where they could literally suck all the air out of this big like oil tank. It's like several stories tall. And they took a feather and a bowling ball and they dropped them from the top of this oil tank about two or three stories high. And since there was no air, they both fell at the exact same rate, even on Earth. So turns out that because of the way gravity works, everything falls at the same rate as long as air resistance can be ignored. And right now we don't know why, right? Well, you don't know why, I know why. People in general know why. We'll learn it in chapter 4. But we're talking about kinematics in chapters 2 and 3. We don't even care about why things work. We want to describe it. And so I got to tell you the answer, right? When you have an object that's falling under the influence of gravity and nothing else, it will always have the same acceleration. Gravity makes things accelerate at the exact same rate regardless. And that rate is called the acceleration of gravity. It has a value. And you will end up knowing that value by heart by the end of this class. The acceleration of gravity, we always denote with a lowercase g. And lowercase g is equal to 9.8 meters per second squared. And of course, it's an acceleration has a direction. The answer is that it's downward. Notice I'm not saying g equals negative 9.8 because depending on my coordinate system, down could be positive or negative. And I don't want to mix you up with that. Plus, what will often happen is we'll have equations later on in the semester where g will appear in those equations. And if you see a g in an equation, you're going to plug in positive 9.8 into that equation. If there needed to be a minus sign, they wouldn't have written g, they would have written negative g. So if it needs to be negative, the minus sign will appear in the equation, and you don't want to double count those minus signs. But this is the acceleration that everything acts under anytime you're under the influence of gravity and nothing else. Now, if there's something else acting on you, like if I'm in an airplane flying through the air, gravity's not the only thing affecting me. The air pushing my wings up gives me a different acceleration than just plain gravity. So anytime there's nothing but gravity acting on you, this is your acceleration, period, end of story, full stop. And that's going to allow us to solve some one-dimensional kinematics problems in a fairly straightforward way. Case in point, let's imagine that I throw a ball straight up and the moment it leaves my hand, it's traveling at a speed of, let's go with 20 meters per second. That's pretty quick. All right. I want to know how high the ball will get. Super easy, fairly straightforward. I'm throwing a ball straight up in the air. I want to know how high the ball will go. Now, this is a one-dimensional kinematics question. It's just instead of the one dimension being sideways, it's up and down instead. So let's draw a picture. So here's a person, I'm throwing a ball, and the moment that the ball leaves the person's hand, it's traveling upward at 20 meters per second. What's going to happen is the ball is going to go up, 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 and eventually it's going to reach a maximum height, and then it's going to fall straight back down. And for convenience, let's go ahead and assume the ball starts at a height of, let's say, 1 meter above the ground. So if I'm solving this problem, I'm going to treat it like any other problem involving one-dimensional kinematics. I've got a picture. I've labeled the stuff that I know. Now I'm going to take inventory of what I know. So I got to pick a coordinate system. So somewhere on this picture, I'm going to call x equals 0. And I kind of like having the ground be x equals 0. That's pretty cool, because now what's going to happen is I can measure all of my positions relative to that spot. Now, I've got 6 things to track: the starting position of the ball, the ending position of the ball, the starting velocity of the ball, the ending velocity of the ball, the acceleration of the ball, and of course, the time that the ball is in the air. So of those 6 things, which of them do I know?
The final velocity,
All right, what's the final velocity?
20, what is that, meters per
Meters
second?
per second?
Mhm.
No. And one way to think about it is, when does it have that velocity of 20? Does it have that velocity of 20 when it's here or when it's here?
When it's going up.
Mhm.
Yeah, it starts off with a velocity of 20. When it leaves my hand, it's going pretty fast, right?
Mhm.
But as
So
soon as
that's
I
the
let go, it's going to start to slow down, right?
Yeah.
Which means by the time it gets up here, it's not going to have the same velocity it started with. So the starting velocity is 20 meters per second.
So I have a question.
Huh?
So with the initial position and the final position, would the initial position be 1 meter or would it be 0? No,
Well,
it'll be 1 meter.
where is the ball when it starts?
It'll be at the 1 meter, right?
Yes, that's right. Yeah. So by calling the ground x equals 0, it won't be starting at 0 because I started it intentionally a little bit above 0.
Okay.
Now, I could have been lazy. I could have called this x equals 0. But then what would have happened was, when I got x final, it would have been the distance from here to there, and I would have had to add 1 meter at the end to get my answer right.
Okay.
Because it wants to know the height of the ball. The height should probably get measured from the ground. That's why I made the ground be x equals 0. That way, when I get x final, it'll just flat out be the answer.
Okay.
So yeah, x initial is the 1 meter above the ground that it starts at, and x final is however high it is from here to there, and that is the thing that I was asked to solve for. Now, what about v final? Do I know the velocity of the ball at the highest point?
No.
I do. but you got to think about it. It's kind of written between the lines. Because I started off with a velocity of positive 20. I'm traveling upward at a speed of 20 meters per second.
So it'd be
Now,
negative 20?
Well, if it was negative 20, it won't be negative 20, because what's going to happen is it starts off at positive 20. I'm going slower, 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 slower. Now, once I start coming back down, it's going to start going in a negative direction, faster, 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 faster. But in order for me to go from positive to negative, I have to pass through 0. And what's going to happen is, at the highest point, if the velocity was positive still, it would still be going up. It would go higher a little bit later. If the velocity was already something negative, then if you rewound time a couple seconds, it would have been higher than it is now. So at the highest point, it's got to be at the place where the velocity just switches from positive to negative. So the velocity of an object is always going to be 0 at the place where it turns around.
Okay.
And so I know that it's got to be equal to 20 or to 0. What's the acceleration of that ball?
Is that 20?
With it. So, okay, so I have a question. It might be a dumb question, but would it have, would it have, I don't know how to ask, but it's like, it wouldn't have 2 separate accelerations, right? Because
well, if I was worried about the time, like while it was in my hand and I'm moving my hand upward to throw it, it would have a different acceleration. But we're starting it once the moment I let it go.
Okay.
And the idea is I've been speeding it up the whole time it was in my hand. Once I let it go, it's already traveling upward at a speed of 20. But once I let it go, what's affecting its motion besides gravity? Nothing. And if only gravity is affecting you, what's your acceleration?
I don't know, dude.
Oh.
Right?
There we go. Okay.
So the acceleration is 9.8 meters per second squared. However, I have up being the positive direction, and it's downward, so I'm going to slap a minus sign on it.
Oh, so this is one of the moments where you say it'll determine. Okay.
Yeah. I mean, it's 9.8 downward, and because I called up the positive direction, then I got to make that be negative. If I did, I'll do a different problem in a little bit, where we'll have down be the positive direction, and it'll be a positive number. Now, how about t? T is the time it takes to go from here to here. I don't know.
We don't know.
Got nothing. So there's my inventory. So to solve this problem, I'm looking for the final position. I need an equation of motion that has the final position in it, but it needs to not have the time because I don't know, nor do I care about the time. So what equation of motion has x final, but not the time?
I'm looking. The V2 equals V initial squared plus 2A with the parentheses of
X.
Yeah, X minus the X initial.
Yeah, this is the one that if I was being snooty, I would call it something like the time-independent velocity equation, but I always call it the stopping distance equation.
Stopping distance equation.
Yeah, because again, I always associate this equation with those problems where it's like I'm driving the car and I see a deer ahead and I'm trying to stop before I hit the deer. And I don't care about how long it takes to stop. I care how far I go because I can't drive more than a certain distance without hitting the deer. So in my head, that's what I always associate this equation with. So there's my equation of motion. There's my inventory. All I got to do is kind of pimp it out for that particular set of starting points. And I like to do all the algebra without plugging numbers in wherever possible. So V final is 0. I can make that be 0. But that's the only 0 I've got. So what am I solving for? I'm solving for x final. So I need to get this by itself. When you're doing algebra, you always do it in reverse order of operations order. So what that means is, like, what's happening to x? I got some stuff inside some parentheses. I got some stuff multiplied by. I got some stuff added to it. So when you're getting x by itself, what I'm going to do is get rid of the added stuff first, get rid of the multiplied stuff next, and do the parentheses last. It's order of operations, but backwards. So first, let's get this on the opposite side of the equation from that. Let's just subtract this from both sides. So I've got I'm going to move this over. So I have negative v initial squared equals, and then on the other side, it's called 2ax minus x initial. So far, so good?
Mhm.
Now I'm going to get rid of the multiplied stuff. Let's get rid of this. So I'm going to divide both sides by this. So I'm going to have negative v initial squared divided by 2a. And then once I've divided by this, I don't even need these parentheses anymore. I can just write x minus x initial. Then I want to get x by itself. So let's add x initial to both sides. So I'm going to have x initial minus v initial squared over 2a equals x final. And now I'm ready to plug in my numbers. So what were my numbers? Well, x initial was 1, so it's 1 minus v initial, so that's 20 squared divided by 2 times, what's my acceleration? Negative 9.8. And notice I got a minus over a minus. That's going to cancel and become plus, which makes sense because my final height should be the 1 meter that I started at plus some extra. So you know I had to have a larger answer than I started with. If I didn't put those minus signs in right, if I screwed the minus signs up, then I would have had a lower answer for my ending height than my starting height, and that makes 0 sense. So it helps to pay attention to that kind of stuff. So I ended up getting 21.4 meters.
Huh? Oh, sorry.
Because you do order of operations, so 20 squared is 400. Then I do 2 times 9.8, that's 19.6. So 400 divided by 19.6 is 20.4, plus 1 is 21.4. So that's how high this guy is going to go. So as problems go, this one's pretty straightforward. And the only new thing that we couldn't have done the other day is we hadn't talked about gravity. So be on the lookout for situations where objects are being affected by gravity and nothing else. Because once you see those, you automatically know the acceleration is 9.8. And I should point out, that's only true if you live on the planet Earth, right? If you travel to some other planet, gravity has a different strength. On the surface of the moon, the acceleration of gravity is about 1.7 or 1.67 meters per second squared. On the surface of Mars, it's like 0.8 something, I think, or 80% less, I think.
Can you show the bottom one more time, please?
With that?
Yeah. Okay. So I have a question.
Yes, ma'am.
So, okay, so you said, where did you change the 1 to be plus that? Yeah, that.
So when I had it generically, I had x initial, which was 1, right?
Mm-hmm.
But it was minus 20 squared over 2a. But what happened was when I plugged in a was negative 9.8.
Mm-hmm.
But that minus sign and the minus sign here became positive.
Okay.
Because I'm doing minus and negative is the same as plus.
Okay, got you.
Yeah. And usually when I have situations like that, rather than type 2 minus signs into my calculator and risk making a typo, usually I'll correct it before I use my calculator because it's easier to do it in my head than it is to do it in the calculator. There's less typing and there's less chances of making a mistake. So that's it for what we call projectile motion problems, problems where you're under the influence of gravity but nothing else. Let's try a different one. Let's try, this one's still damp. Let's try so I've got a dude standing on the top of a building. All right. And what he's going to do is he's going to reach out over the edge of the building and toss a ball straight up into the air. At, let's say, 20 meters per second. Right. Meanwhile, back down on the ground, his friend has a gun and he shoots a bullet upward at the ball. At 300 meters per second, which is roughly the speed of a bullet. It's a slow bullet. Right. So basically, it's like the guy is doing skeet shooting. One guy throws the target up into the air, and the other guy is down on the ground, way, way below, shooting straight up into the air. And what I want to know is, how high is the object when it gets shot? So what this is doing is it's kind of combining the example we just did with the example from right before that, because it's in a lot of ways very similar to that Velociraptor question. So let's figure this out. And so here's my big tall building, and here's my dude with the target at the top. And here's my dude at the bottom with the gun. And he's going to shoot his bullet. The bullet's going to go up. The target's going to go da 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 da. And somewhere the bullet and the target are going to be at the same height. And for simplicity's sake, the building is 50 meters tall. Let's ignore the height of the people and just assume that the height of the people is negligible. It turns out they won't make much difference to our answer anyway, and it just makes the math more annoying. So to solve this problem, I've got two objects that are moving. I've got the object that he threw and the bullet that he shot. They're both moving, which means just like in the Velociraptor question, I'm going to have to break down and do an inventory for both the bullet and for the ball. Let's do the ball first. Now, before I can do this inventory, I have to choose a coordinate system. So somewhere on this picture, I have to put x equals 0. I like putting x equals 0 at the ground. So if that's the case, what is the initial position of the ball?
Is it at 50 meters?
Absolutely. He started off at a height of 50 meters. That's correct. So X initial is going to be 50 meters. Now, what about the final position of the ball? That's how high the ball is when it gets shot.
So the same, right?
Not necessarily the same, because remember, how high it is when it gets shot is the thing we're looking for. So we don't know, right? This is the answer to the question. Now, the initial velocity of the ball, do we know what that is?
Is it 0?
It's not 0.
No.
Because in the problem, it says the person tosses the ball upward at 20 meters per second. The moment that guy throws the ball leaves his hands, it's traveling up at 20. So that's my starting velocity. Now, the ending velocity, I don't know. Because what's going to happen is it's possible that the guy throws the ball up, and while the ball is still traveling upward, the bullet catches up with it and hits it. So maybe it's still on its way up and it gets shot. Could be. Maybe the ball gets all the way up to the very, very top at that moment when it's briefly got a velocity of 0, and that's when the bullet catches it. Could be. It's also possible that it takes so long for the bullet to get up there that the ball has time to go up and start to come back down again, in which case the velocity of the ball would be something negative as the bullet hits it coming up from the bottom. We don't know. So what's going to happen is the final velocity of the ball, I have no clue about. What about the acceleration of the ball? What is the acceleration of that ball?
Would it be 9.8 again?
It would be 9.8, except it's 9.8. If this is x equals 0 and this is x equals 50, the positive direction is upward. Slapping a minus sign on it. And then t is however long it takes for this guy to get to there, which we don't know. So in that inventory, there's 3 things I don't know: the final position, the final velocity, and the time. How about the bullet? Which of those things do we know for the bullet? So remember, x initial is where the bullet starts. How high is the bullet when it starts? Well, what's the position of this? X
0.
Now, x final. How high is the bullet when it hits the ball? Still don't know. Remember, that's the thing I'm looking for. So it appears in both inventories. That's a clue. V initial, that's the velocity of the bullet when it first comes out of the gun. So how fast is the bullet traveling when it first comes out of the gun?
300 meters per second.
300, yep. Now, the final velocity is the bullet velocity just as it hits the ball. And I don't know what it is. I do know that as it rises, it's slowing down just like anything else because bullets are affected by gravity. You just don't notice so much because they're traveling so freaking fast. So V final, I don't know, but it's probably slower than 300, but bigger than 0. What's the acceleration of the bullet?
The same as the acceleration of the ball.
Yes. Why? Because it's affected by gravity and nothing else. So, ha. And of course, the time, still don't know it, but however long this guy takes to get shot is how long this bullet takes to get to him. So the times are going to be the same. So it's very much in the same vein as that velociraptor question. It's just vertical and not horizontal. So when I go to calculate my answer, I'll do the same trick. I'll make an equation of motion for the ball and another one for the bullet. And I want to use equations that have things in common. So I'm intentionally choosing an equation that has both x final and t, but I'd still want to avoid the other velocities that I don't know. V final is bad. Which one does that use? This is my generic equation. X final equals X initial plus V initial t plus 1/2 a t squared. That's what I call the position equation. It's useful to us because there's no V finals. And I'll do it once for the ball, once for the bullet. So for the ball, and because there's so many different X's, I'm going to go ahead and plug the numbers in here early because it makes it easier, I think. So for the ball, I've got X final, which I don't know, X initial, 50, plus V initial, that's 20 times t, minus or plus 1/2 times negative 9.8 t squared. So that's the equation for the ball. Meanwhile, the equation for the bullet is X initial is 0 plus 300t plus 1/2 times negative 9.8 times t squared. So just like that stupid velociraptor question, I get two equations with two unknowns. And heck, I could do the same trick for solving them, because if x equals this junk, but x also equals this junk, that implies that this junk is the same as this junk. So I'm going to set this equal to this. I went ahead and just took 1/2 times 9.8 and got negative 4.9 for both of those. Except this is the easiest problem ever, because check it out. If I have negative 4.9 t squared here and negative 4.9 t squared here, if I add 4.9 t squared to both sides, this cancels this. Convenient. I don't even have to do a quadratic for this. Now I've got 50 plus 20t equals 300t. Let's get the like terms together. Subtract 20t from both sides, and I have 50 equals 280t. So I know how long it's going to take for that bullet to strike, and that's, we'll call it 0.1786 seconds. That's how long it's going to take for that bullet to strike. Now, if I want to know how high that is, all I've got to do is take that value for t and plug into either of those two equations. And it doesn't even matter which one. I'm going to use the second one just because there's less going on. There's two terms. So my final answer is going to be 300 times 0.1786 minus 4.9 times 0.1786 squared. and I get a whopping 53.4 meters. So what's going to happen is the ball started at 50 meters and it went about another 3.4 meters above, and bam, it gets shot. So it looks like it's going to get shot on the way up. Kind of cool. Hopefully that's super easy. You guys feel like you're pretty well equipped here? Because at this point, that's all the stuff we got from chapter 2. All right, so tomorrow we'll start chapter 3, vectors. If you wanted to get super ahead of the game, you might try reading, I think it's the first 3 or 4 sections of chapter 3. It's always good if you've read ahead, because that way you'll be able to, like when you spot in the book things that are confusing, when I talk about them in class, you'd be like, oh, that was the thing I didn't understand, and you can ask questions about it. You'll retain things better if you kind of prime the pump a little bit by reading ahead. So we're definitely going to start chapter 3 next time. And that means we're going to have to invent a new kind of math, because keeping track of the direction is easy in one dimension where I only have 2 directions to worry about, left or right, up or down, positive or negative. But with things that are moving in diagonal directions, there's a whole bunch of different directions to choose from, and plus and minus isn't going to cut it anymore. We're going to have to invent some new tricks to keep track of all that stuff. But we will do that next time. Do your homework, and I'll see you guys tomorrow.
Bye.
Bye, guys.